Hello everyone, I'm Jakob Jørgensen and I'm here to present our work GPU in Sky, a GPU parallel algorithm and tree structure for efficient density-based subspace clustering. The work is done in collaboration with Katrine Seel and Ira Assen from Aarhus University. Subspace clustering is the task of grouping points within all possible subspaces of the full dimensional space. However, the number of possible subspaces is exponential in the number of dimensions and therefore takes a long time to perform. Most subspace clustering algorithms are traditionally developed for the CPU and does not utilize a multi-core architecture such as the GPU, which would provide a high computational power through thousands of cores. Our goal is therefore to construct a GPU parallelized version of the dimensionality unbiased subspace clustering algorithm InSky that we call GPU InSky. InSky is a density-based subspace clustering algorithm similar to dvScan and subloop that makes this subspace clustering unbiased regarding dimensionality by normalizing the density criteria by the expected density of the subspace. InSky prunes points by weak density, meaning that they prune points that would not even be dense for the full dimensional space. Furthermore, InSky introduces a redundancy factor where they say that a cluster in a subspace is redundant if there exists a cluster in a superspace that covers more than a fraction of the points. InSky uses this to prune regions that does not contain enough points to contain a non-redundant cluster. The regions are constructed by splitting each cell into by splitting each dimension into cells, each with a border of size epsilon. If there is a point within this border, it is likely that a cluster would span multiple cells and they are merged into one region. As we expand into higher dimensional subspaces, we split each region into multiple cells along the added dimension and perform the same process of merging cells that contain points on the border. InSky speeds up computation by using an indexing structure called the sky tree. The sky tree represents everything within a region that has not yet been restricted. The sky tree is organized in layers with one layer per not yet restricted dimension and node for each cell on that dimension. Each node contains the cell number and the count of points within that cell. If there exists a point within the border of that cell, we construct an S-connector path starting from that dimension and containing the associated cell numbers. The sky trees is now used to restrict and merge cells with S-connections. This is done by identifying the cell that matches the dimension and cell number, covering everything above and below in the tree. This is done for all nodes matching the dimension and cell number. If we match the start of an S-connector path, the cell must be merged. This is done by restricting according to the next cell number, and the two trees are then merged into one, where we merge all nodes that has the same parent and cell number. The algorithm proceeds as follows. For each pair of dimension and cell, we restrict the cell and merges with the neighboring cell if there exists an S connection. We prune for weak density before calling recursively to find the clustering in the superspaces. We then return and have found all the clustering in all superspaces, and we can therefore check if there already exists a clustering that would make the current region redundant. If not, perform clustering within this region. InSky is a nice algorithm, but it is still slow, and in our own experiments, it takes 2 hours to find a subspace clustering of just 4,000 points. In short, our contributions is then a GPU parallelized dimensionality unbiased density-based subspace clustering algorithm called GPU InSky. This includes an efficient clustering search and indexing structure for the GPU. To achieve a high parallelism, we identify the most time-consuming tasks and restructure them such that they can be performed in parallel. We first observe that restrict and merge does not depend on any other operations, and we can therefore perform them right at the beginning. Next, we observe that the neighborhoods are used both for pruning and clustering, so we pre-compute this. We then perform all the pruning steps, but wait with the clustering until the very end, such that clustering of each region can be performed in parallel. For GPU InSky, we construct a GPU-friendly version of the sky tree called GPU sky tree. Instead of representing each node as an object, we keep an array for each attribute, parent pointer, cell number, and count of points, where each node is represented by an entry in each array. We arrange the layers one by one in the arrays to ensure memory alignment later. When restricting, we need to allocate the restricted skytree in one go instead of one node at a time. To do this, we keep an array called include, where we mark for each node if it should be included in the restricted skytree. We then compute a prefix sum to obtain the indices for each included node in the restricted skytree. Next, we observe that each restrict operation only read from the input and are therefore independent of each other and can be performed completely in parallel. We also observe that each node on a layer does not use any information of the other nodes on that same layer, and we can therefore handle each node on a layer in parallel. However, each node must know if either its children or parent are included, which gives us a dependency between layers. This leads us to 4 different kernels where we handle each slightly different. For the layer just above the restricted dimension, the rest above, just below, and the rest below. And we now know which nodes are included, the new indices, and the count of points in each cell. We can therefore allocate space for the new skytree and copy everything in parallel. We now need to merge, but we cannot perform all merges in parallel since we need the result of the previous merge. However, we observe that merges only depends on these S connections. And we therefore propose to pre-compute which skytrees are merged and use this to restrict the final merge result right away. We first compute a table that marks if there exists an S connection for all pairs of dimensions and cells. And we use this to pre-compute what we call a merge map, where we identify a merge sequence by the cell number that starts this sequence. We can now use this merge map to check if a cell would have been merged into the skytree instead of matching with just the current cell. We also need to remember to merge identical node. For nodes above the restricted dimension, all identical nodes we need to merge before would have been copies of the same node, and therefore nothing needs to be done now. For the identical children below the restricted dimension, we would still need to merge since we have deleted a layer, which means that we can now have identical children. To keep track of the representative nodes, we introduce 2 new arrays, the new parents and the new children. For merge nodes, we must pick a representative. This is done by letting all nodes write its own ID as the new child and synchronize such that all nodes agree on which one have been picked. For the clustering, we base our clustering on the already GPU parallelized version of dbScan called gdbScan. Like GPU NSky, this version also pre-computes the neighborhoods by first finding the sites of each neighborhood, allocating space, and populating the neighborhoods. gdbScan now expands one cluster at a time by repeatedly checking all points in parallel to see if they can expand the current cluster. NSky also pre-computes the neighborhood, but furthermore uses the neighborhoods of the subspace to bound a search in a superspace efficiently, reducing the number of distant computations by a large factor. Extending cluster can be done in parallel across all regions, and furthermore, we also change the algorithm such that we expand any cluster in parallel instead of just a single cluster. This is done by assigning all points to a singleton cluster and then expanding the cluster with the smallest ID that can be reached by the neighborhood of each point. Comparing to NSky, we clearly see that GPU NSky achieves a much larger speedup. In fact, at up to 15,000 times, which is surprisingly large. We suspect that the bounding of neighborhood search would provide a large speedup due to the low number of distance computations and not just a high parallelism. We have therefore created a version called GPU NSky Star that does not bound the neighborhood search in any way. This version only achieves a factor of 500 to 1,000 times, which is much more realistic. We provide our code at GitHub. Thank you all for listening.